Great, great. Welcome everybody to this session about time and sequences. And we have 6 challenging papers, 2 VIS papers and 2 TVCG papers. And I'm looking forward to the first presentation, which will be given by Peilin about revealing interaction dynamics, multi-level visual exploration of users' strategies with interactive digital environments. Peilin, the floor is yours.
Thank you very much. All right, hope you all can hear and see my slides.
Perfect, perfect, perfect.
Great. So hello, everyone. As you know, in today's digital learning environment, the use of large touch screen displays is becoming increasingly common. But have you ever wondered, how do these public visitors actually interact with these devices? Understanding this is both interesting and important for improving engagement and learning outcome. Our goal in this work is to first study how individuals interact and engage in interactive digital environment in an informal learning setting. And 2, to explore whether or not we can identify exploration strategies that correspond to different levels of learning processes. To achieve this, we formulate a set of tasks in an experiment that reflect different levels of learning processes to be performed in a digital environment. We then conduct this experiment using a public exhibit to collect interaction data. And finally, we design a visual analytics system to analyze this data that we have collected and identify the exploration strategies. And today, I'm pleased and humbled to be presenting our work. My name is Peilin from Linköping University. Over the past 12 months, experts in visualization have collaborated with experts in visual learning and communication. And together, we embarked on a journey to address the aforementioned objectives and to achieve our goal. As previously mentioned, the background of our work is set in the context of public space learning environment. You might also know it as informal or out of classroom learning environment. But why? Why should we care? Why is this important? Such learning environments are important because they facilitate scientific communication. They generate interest in STEM, which stands for science, technology, engineering, and mathematics. And most importantly, they raise awareness about societal issues such as climate change and gender equality. It's even more critical to investigate this matter because this kind of environment, they rely on the visitor's own interest. And on the other hand, it also depends on how engaging, how well designed an exhibit is. And therefore, we need to design meaningful and engaging interaction techniques for visualizing, understanding, and communicating data. It is then in our interest to gain insights into how visitors interact with interactive systems. And now comes the question, how? How do we do that? How do we gain insights into how visitors interact with interactive systems? Well, it's a common practice to log the interactions between the visitors and the touch screens. This results in interaction event sequences that can reflect the exploration approach taken by the visitors. And existing work that leverages visual analytics to analyze such data has limited application in educational or learning settings. Our goal is then to bridge this gap. Our goal is then to explore the user behavior and interaction strategies in order to reveal how users engage with digital environments. To this end, we propose a visual analytics approach designed to assist and support domain experts in the interactive exploration of interaction log, as well as coupling interactions with cognitive learning processes. This then led to a series of workshops where we distilled a set of system requirements and tasks, which then led to the production and design of the prototype VA system. After that, we conducted a case study using one of the public interactive exhibits named Sweden in Numbers, which contained demographic data about Sweden. In the next slide, you will see a short clip of a user using this exhibit. And in this exhibit, we are referring this bubble-shaped element as an info panel, which is tied to a municipality. Below, those are the 4 different categories, including age, education, income, and population, which will produce different types of info panels. All right, now let's take a closer look at the prototype system. Here's an overview of the interface. There are 3 main things to highlight here. First, it facilitates the exploration of interaction at the individual user level. On this level, each bar represents an interaction on an info panel. The line represents the attribute change sequence. And in this exhibit, it can be gender, it can be year, and it can be municipality. The different colors represents the different categories, the 4 different categories in the exhibit, as you saw in the previous clip. Additionally, it also supports multi-user comparison. And here, to overcome the scalability issue, we display only the category of the info panel and overlay it, superpose it with the attribute change sequences. The second thing to highlight, it facilitates the exploration of interaction at different granular levels. So for example, this is what we have defined as the high granular level, whereas previously you saw the interaction sequences, which is what we have defined as the low granular level. On the high granular level, now each bar represents the entirety of the info panel. And on this level, you can investigate concurrent active info panels. Last but not least, the system is equipped with algorithmic support to compute the similarity of individuals' interaction sequence using dynamic time warp and apply hierarchical clustering to detect exploration strategies. Now, to demonstrate the usefulness and applicability of our approach, we perform an experiment involving 14 participants using the Sweden in Numbers exhibit. And in this experiment, we asked the participants to complete a set of tasks that we have designed with increasing complexity to stimulate different levels of learning, of cognitive learning processes as introduced in Bloom's taxonomy. Bloom's taxonomy is a standard framework that is used to categorize learning goals. And there are 6 levels introduced as displayed in the second column. We then have formulated the tasks in this experiment to reflect the different levels. Now you don't have to read through the whole thing. I put it up just for the sake of completeness. However, you can find the full table in the paper itself. And last but not least, in the last column, these are the exploration strategies that we have discovered using our VA system. And here I'll quickly show you one of the examples. The question was, which municipality in Halland has the highest average salary for women in 2017? Halland, which is a Swedish county. And here are two different strategies that we have discovered using our VA system. Each figure represents a single participant. Again, each bar represents an info panel, which is a municipality. The line is attribute change, and in this case, it relates to gender. This is the equivalent in the exhibit. Info panel, municipality. In each info panel has several attributes, including the gender. Coming back to the VA system, what we are seeing here is that the user open up an info panel related to a municipality, and by default, the gender is set to both. What they did next is that they change the attribute from both to female. And this action is repeated several times, which created this kind of cascading pattern in our VA system. And this is how the strategy looks in the exhibit. Notice how they never needed to revisit the previously opened info panels. I'll quickly skip through these slides since we don't have time. So to wrap things up and to summarize, the contribution of this work include the definition of the set of requirements for informal learning environments to understand users' exploration strategies. We propose a VA prototype system which supports multi-level and multi-granular exploration of event sequence data. And finally, an application scenario where we collected a real-world data set and performed a case study to demonstrate the usefulness and applicability of our proposed approach. So thank you very much for your attention. And if you'd like to know more about our work and play around with the system, feel free to visit this URL, and you will find several QR codes on screen right now that will take you to different places. Once again, my name is Peilin. Thanks for having me.
Thank you very much, Peilin, for this nice presentation and this really nice, impressive approach. I'm really sorry you took over all your 12 minutes. We don't have any time for discussion. I'm really sorry for this. But there is one announcement, one question. A person is really, I like the pace in which you speak. Yeah? This is just to give you feedback. What a nice presentation you have. Thank you, Peilin, again. Thank you very much. It's a really great piece of work. We come to our second talk, and the second talk will be given by Tim Krake from the University of Stuttgart, as I'm correct. And this time we will deal with uncertainty-aware seasonal trend decomposition based on Loess. Tim, the floor is yours.
Yeah. Can you see my slides? Can you hear me?
Perfect. Everything is fine.
Perfect. Okay. So hello and welcome to my talk about uncertainty-aware seasonal trend decomposition based on Loess. My name is Tim Krake, and this is joint work with Daniel Klötzl, David Hägele, and Daniel Weiskopf. And before I dive into our main topic, I want to provide you a small motivation or problem description. So for those who are not familiar with seasonal trend decomposition based on Loess, in short STL, here's a visual overview. So in general, we start with time series data. Here you have the trend component and seasonal components, which are then initialized. And afterwards, we have an outer and inner loop in this algorithm. And the inner loop consists of 6 steps. Later on, we will explain a little bit more what these steps does. And afterwards, these 6 steps and the posts moving lead to our desired components, which are a trend component, a seasonal component, and residual component. And here on the left, you have an example. Here we have some input data. You have a trend component, seasonal component, and residual component. This is an additive decomposition. And the seasonal component is determined by a period, which is user-defined. And yeah, this is state of the art, which is given in the current state. But we ask ourselves, what can we do if we have some input data which is uncertain? So in this case, we have a discrete Gaussian process. You can see it on top left. And this brings up the question, how can we compute the trend component, the season component, or the residual component now? And this brings up 2 different challenges. So first of all, a mathematical challenge, which is uncertainty propagation through the pipeline of STL. and also some, of course, some visualization challenges, which are the correlation in each STL component, how we capture this, and specifically in this case, because we have a decomposition, also the correlation between the STL components. We start with the mathematical challenge, but before we do that, I want to explain where uncertainty actually comes from. And in our paper, we introduced or we presented 3 different application scenarios. So first of all, we have this kind of ensemble data when you have multiple samples and you want to deal with them all in one sense. So for example, you can then estimate the Gaussian process out of it. Here we have then a mean and a covariance matrix. And this is one scenario. This is the estimation of a Gaussian process due to sample data. What we also have is a modeling effect. If we have some data and we want to model something on top of it, then we can do that via kernel functions. We have presented a first application scenario that is data with uncertain areas. So if you have some data and you are not sure if some areas are really certain, then we also propose a technique how you can put some uncertainty on top of it, as you can see in this example. And we also have a second application scenario, which is data with missing values. This is a quite common scenario. Here we have a proposition how you can model the mean and also a covariance matrix. But I don't want to go into too much details. Please refer to the paper if you want to more about the mathematical details, how we do this. So now let's tackle the mathematical challenge, the uncertainty propagation through the pipeline of STL. As we have seen before, this is the visual overview of the steps, what STL does. And now we want to go through each step and explain that each step is indeed a linear procedure. So the step 1, there is some subtraction going on. In step 2, we have simply a periodic extension, which is also linear. Then we have a smoothing in step 3, that's also linear. The next steps covers subtraction, addition and subtraction, and finally in step 6, there's also a smoothing. And all of these steps, all of these 6 steps in the inner loop are indeed linear. And the final step, the post-smoothing, is linear as well. And this leads to our trend, season, and residual components. And in sum, all of these steps, the outer loop, the inner loop, the post-smoothing, are a linear procedure. And this is exactly the idea behind our technique, that we in the first place showed that the STL is really a linear procedure, which means that if you look at the top right, if we start with our time series data and we have the trend, seasonal, and later on we also initialize the residual component. If we have this as input, and our output is, of course, the desired trend, seasonal, and residual component, then there exists a big matrix A which connects these kind of components. So which maps our input data to our trend, seasonal, and residual component. And this matrix A can now be used to follow the same procedure for uncertain data, which means if we have some input data which is uncertain, in our case, we assume that it's normally distributed. We have a mean vector mu and the covariance matrix sigma. Then we can use this matrix in the same procedure. So first of all, we do an embedding. So the mean vector is embedded and the covariance matrix is embedded as well. All of these components, this is kind of the initialization step, which we have seen before. And all of it is initialized with the value 0. And now we have the right dimension to apply the matrix A. And this will lead to the linear transformation of our expected mean and our covariance matrix. And then you have this result. So we have an output, and this is mathematically exact, that we have an exact uncertainty propagation through the pipeline of STL. And this is the mathematical challenge. So this is done. Now we are focused on the visualization part. So we have to deal with these output data. We have the expected mean, and we have also the covariance matrix. And again, we want to tackle for example, here specifically the correlation in each component and between the components. So now we look at our, let's say, we mentioned this, the core visualization or overview visualization. You might have noticed that we also use some isoband structure and we use some spaghetti plot. But in this case, we use a specific spaghetti plot, which is color-coded. This is due to the fact that we have here STL-consistent samples. For example, if you look at the purple line, you can see that in the input data, where the arrow points to, that is a little bit above the mean. The mean is in dark blue. And then you can see that it's really an STL consistent and an actual STL decomposition. So you can see it in the trend component. It's a little bit above the mean. And because in the input data, the purple line is a little bit out of the periodic effect, then you can see that the seasonal component is quite confused a little bit. And this is really correctly displayed here. So all of these color-coded plots are actual STL decompositions, and therefore we color-coded and highly propose to do that. Besides our core visualization technique, we also have some correlation exploration. So first of all, instead of using the covariance matrix itself, we propose to use the correlation matrix. And here also we use the discrete color coding, and also to integrate this correlation matrix into our overview or core visualization, we put a column, a specific column or specific row. The matrix is symmetric, so it doesn't matter, under each plot in each component. So you can see this black bar highlighted by this orange box. You can see that we want to highlight the specific column, which is here highlighted by the dotted line. And then you can, for example, see that this point in the input data, how it correlates with, for example, the seasonal component with period 7. And you can see the blue and the red area that it positively and negatively correlates. What we also have done is an alternative representation of the correlation matrix, which kind of highlights, which we call the correlation length. So this correlation length is displayed by this alpha value, just that you get an idea out of it. So you have this dashed line, you have this alpha values, and this correlation length points to the left and to the right, exactly as long as the first negative or zero value correlation value in the correlation matrix appears. So with this, you can see abrupt changes in the correlation matrix. Besides the correlation exploration, we also have some sensitivity analysis. And here we have two second ways how to deal with it. First of all, we support some Gaussian distributed kernel, and this shows how uncertainty changes impact our decomposition components. So we change the uncertainty by the Gaussian distributed kernel, and then you can see with these dotted lines how the uncertainty changes in the components. But we also support a customized kernel, which you can draw on your own. So you have also this kind of effect, how this changes the uncertainty in our components. And here you have a small video which shows how this can be done in an interactive manner. So you can see that the black bar slides from left to right in our input data, and it shows how the uncertainty is affected in our, for example, seasonal component 2 or residual component. This brings me to the end of my talk. Thank you, and the source code is also available on GitHub.
Thank you very much, Tim, for this very, very nice, impressive presentation. We have time for a quick question, and there is no question in Slido, but I have a question. I was listening to Daniel Weiskopf's talk in the workshop about uncertainty, and he was mentioning there having tasks in mind is very, very important. Can you think about which kind of task did you have in mind when you designed this solution?
Yeah, that's a good one. So in general, STL is used for 3 different tasks. So for example, there is in general the analysis of periodic patterns. And if you have something like many samples from something, then you can estimate a Gaussian process, and then you can apply our technique that you get this kind of overview representation. I didn't have time for that, but we also covered it in our paper where we deal with some sales data, and then we have also this kind of user study. Then you can maybe look into that, and you can see that it helps the perception of these general patterns. But also another task, what STL often is used for, is prediction. So this could be also a possible application that we use STL for this general prediction topic. And also here I can see that UA-STL, our technique, could help and you could benefit from it.
Thank you very much. Thank you very much, Tim. We are a little bit out of time. There are a couple of questions now in Slido. I would ask you to answer them in Discord. Thank you very much. We are coming to our third presentation, and the third presentation is given by Kazi, Tasnim, Zinat, and it will deal with a multi-level task framework for event sequence analysis. Kazi, the floor is yours.
Thank you. Okay, so let me share my screen first. Can you see my screen?
It's coming, it's coming. Yeah, we see it. Everything perfect.
Okay, should I start?
Yeah, please.
Okay. So hi everyone, I'm Zinat and I am a PhD student in the Human Data Interaction Lab at the University of Maryland, College Park. And today I am excited to present my work titled A Multi-Level Task Framework for Event Sequence Analysis. Event sequences are all around us. For instance, vehicle maintenance. Every time a car gets serviced or repaired, that's an event in a sequence of the vehicle's lifetime. In healthcare, patient medical records are complex sequences of diagnoses, treatments, and outcomes. In every sport, there is a sequence of player actions and game events. And in e-commerce, every click a customer makes on a website forms part of a sequence that can reveal insights about user behavior. These diverse examples show just how ubiquitous and important event sequences are in our data-driven world. To address problems from these different domains, researchers have developed numerous systems. Here, we see examples of 4 different systems being applied on these 4 different problems. Each system often comes with its own custom visualization and unique analysis techniques. While this diversity is great for solving specific problems, it creates a challenge. How do we compare these tools? How do we learn from previous approaches when they seem so different? This is where task abstractions come in. Task abstractions are theoretical frameworks that characterize and categorize visualization tasks. We can think of task abstractions as universal language. It converts domain-specific problems into general visual analytic tasks. With this language, we will be able to make meaningful comparison between tools, adapt lessons learned from previous tools more easily, and even guide the development of new, more versatile tools. Therefore, we want to create a task abstraction framework with the vision to help researchers like us gain a deeper understanding of domain expert requirements. This framework will also provide guidance to domain experts for choosing visualization systems for their specific problems. Now, let's take a brief look at some previous task taxonomies for event sequence analysis. Plazo et al. Proposed 8 high-level user tasks for event sequence analysis. However, it only provides high-level goals and do not shed light upon how to translate them to low-level tasks. Du et al. Identifies 15 strategies for data reduction. However, they do not cover tasks unrelated to data reduction, such as visualization and provenance. Peilin et al. Describe the tasks in terms of action, target, and criteria triplet. While they address the multidimensional nature of tasks, they do not cover the hierarchical view. While all these works are important steps towards task abstraction for event sequences, there is still room for improvement. In our paper, we present a multi-level and multidimensional task framework for event sequence analysis, providing a structured approach to map analysis goals to visualization and data manipulation techniques. Now, we will see the conceptual structure of our framework. Our framework covers both multi-level and multidimensionality. Here, the multiple levels or hierarchy is defined with 4 levels. The lowest level technique is described using 4 different dimensions: the action, input, output, and criteria. Now let's dive into how we developed our framework. We first captured papers from top HCI and visualization venues and analyzed 58 papers representing 52 unique systems. After assembling the corpus, we extracted tasks from the papers. First, we identified relevant clauses. For example, this sentence is from CoreFlow, published in Eurovis 2017. And It consists of two following clauses. Users drill down to a link and compute branching patterns on subsequences in that link. Then we characterize the tasks based on 4 dimensions. Let us go through an example to understand how these 4 dimensions work. Here we can see a clause from core flow which describes extracting branching patterns from event sequences. We identified the action, which in this case is extract. Then we identified the input of the action, which is event sequences here. The action resulted in an output, which is branching patterns. And finally, we identify conditions for this action, which is the rank, divide, trim algorithm. This forms the lowest level of our framework techniques with these 4 dimensions: the action performed, the input, the output, and the criteria. After task extraction, we organize them into building blocks to form the hierarchy of our framework. We organize the techniques with 4 dimensions into groups based on similarities in action and data components. For example, both identifying common patterns and extracting latent patterns output summary patterns from sequences. Therefore, we group them as summarize. This led to the higher level structure called strategies in our framework. We then further group the related strategies based on the reason or why behind each analysis step. For example, we summarize and aggregate with the intent to simplify data. This led to the next level in our framework called the intents. Finally, we identified the overarching objectives of the entire analysis process. Here, let's look at what the levels of our framework look like. At the top, we have objectives. These are the big picture goals of the analysis. Next, we have intents. These are the purposes behind each analysis step. Then comes the strategies. These are the methods we use to achieve our intents. Finally, at the lowest level, techniques are the specific actionable steps we can take. As we can see, the tasks get more and more specific as we go down the hierarchy. So how do all these levels come together in our framework? Here is our task framework with all the details. It might look a bit intimidating at the first glance. Therefore, we are going to walk through an example to show how it works in practice. Let's look at an analysis question where marketing analysts want to figure out what leads to successful purchases to demonstrate the application of our framework. The high-level analysis goal here is to identify successful customer journeys. And we can do that by exploring the common patterns. Therefore, the objective here is pattern exploration. Now, an analysis process is made up of multiple steps. Therefore, let's take one step from this analysis as the running example that we have previously seen, where we are converting the sequences into pattern. We reduce the amount of data by converting sequences into pattern. Thus, the intent is data simplification. Within simplified data, we have 3 strategies: aggregate, summarize, and segment. In this specific use case, we are using a sophisticated summarization algorithm instead of manual aggregation. Therefore, the strategy here is summarize. Finally, the algorithm produces branching patterns that are present in the original data. Therefore, the technique is common pattern extraction. Now, let's revisit the individual dimensions of the common pattern extraction technique. The action is extract, our input is event sequence data, the output is patterns, and finally, we have the criteria, which is the recursive rank divide trim algorithm along with specific mining parameters. This tells us exactly how we are performing the extraction. By breaking down the tasks this way, we can describe any task in event sequence analysis. We evaluated our task framework using 2 key concepts: expressivity and coverage. Expressivity is the depth and detail of information provided by the framework for each task. High expressivity allows for precise task and guidance for implementation. Coverage is the breadth of tasks that the framework can effectively describe across the entire analysis pipeline. High coverage ensures applicability to diverse scenarios. Better expressivity and coverage ensures comprehensiveness. Therefore, our framework aims to maximize both expressivity and coverage. To evaluate our framework, we codified 3 different case studies from 3 different papers and compared them with the previous task taxonomies. From our evaluation, we see that our framework provides a more comprehensive and precise description of the task, capturing both the high-level intent and specific implementation details. We also see that our framework is capable of capturing a wide range of tasks, especially related to provenance and visualization that are often overlooked by other taxonomies. To sum up, our main contribution is a comprehensive multi-level task framework for event sequence analysis. It captures the unique complexities of event sequence data, such as temporal orders, variable lengths of sequences, and hierarchical structure. Second, we provide multiple levels of abstraction. At the top, we have the high-level objectives. Then we break down the steps into intents, strategies, and specific techniques. This hierarchical approach allows us to connect abstract goals to concrete actions. Third, our framework covers end-to-end analysis workflows. We are not just looking at visualization tasks, but the entire process from data preprocessing to insight generation. Finally, we provide both a multi-level and multidimensional view of tasks. This means that we can describe tasks in great detail, specifying not just what is being done, but how, why, and with what parameters. In essence, we created a versatile framework capable of expressing any event sequence analysis task. This can help researchers compare different tools, help developers create more versatile systems, and help analysts choose the right tools for their specific needs. Thank you so much for listening to my talk. I will leave this framework screen open as the questions come in.
Thank you very much. Thank you very much for this impressive framework and the tasks. The framework, what is really impressive. We have we have time for one short question. And the question, what I would select it, the question is, when tasks are extracted from the literature describing existing techniques, there is a risk of missing important tasks that are not yet supported. Any thoughts on this?
So basically the question is asking, like, when we are extracting tasks based on like existing techniques, if they're like, whether we are missing tasks. So
Exactly.
I think, yeah. So basically when we were extracting tasks, we just extracted the clauses. And then from the clauses, we actually had like, yeah, you were right that there could be like a risk. So that's why we codified this using like, we had 3 people to codify this. So we did it individually, and then we talked with each other to identify like if there are any new tasks or like if the tasks make sense or not. So I think like that is how we tried to mitigate this. But yeah, definitely there is like a risk.
Thank you very much. We are really running out of time. There is coming in additional questions. I would like to ask you to read them in Discord and answer them in Discord. Thank you very much, Kazi, for this nice talk. Now we are moving to a TVCG paper, which will be given by Jürgen from the University of Zurich. It's about visual analysis of time-stamped event sequences. We are still.
Hi, Sylvia. Hi, everyone. Can't wait. Oh, yeah, now the screen share is free. And it is now supposed to be up.
Yeah, we see everything. Everything is
Fantastic.
fine.
Yeah, we are moving to TVCG, but we are staying in the realm of event sequences, to be precise, time-stamped event sequences. It is 3 years ago when Ben and I was sitting in Vancouver in a Mensa for lunch and had the idea, wait a second, there's a blind spot in time-oriented data and event sequences analysis. And this is what I want to talk to you. And happily, together with 4 of my great students at UZH, Clara, Eduard, Andrea, and Yasara, by the way, Paris, the one who was just referred to in the Taxonomy 2022, did this work together. Okay, here we go. Coming back to this blind spot, every one of you knows categorical time series, where some category changes over time, univariate time series where numerical value changes over time, or multivariate time series where many things change over time. But there is one thing that is sort of forgotten here, which is time-stamped event sequences where no value changes over time. It's simply the occurrence of time and the patterns that exist just from this particular temporal signature. And this is a very interesting one because it happens everywhere. It is about heartbeats. You can encode personal workouts. You can encode social media events, earthquake aftershocks, code repository commits. You can encode everything with time-stamped event sequences without the need for values, just caring about temporal signatures and decision-making based on this. Interestingly, in visualization research, there's a lot done for the latter 3, and you all are very much aware of it, but not so much about time-stamped event sequences. This is why I want to do this. Just for the sake of completeness, we will refer to some abbreviations in the paper and also here in the talk to keep things a little bit shorter. And I will simply call them sequences, but it is on timestamped event sequences. Coming to the challenges, first of all, there can be thousands of these sequences, and each of these 1,000 sequences could have thousands of events, which makes it complex in millions of individual events that people may want to analyze. Coming from that data-centric complexity, there is more that can add to the challenge space. For example, the lack of metrics. Ben introduced me to the world of metrics that do exist for such event sequences to actually make more sense from individual subsequences. The contextualization of patterns is something that you need if you want to make sense from things. For example, if I find something, I would like to see if it is occurring, for example, with temporal occurrence or spatial occurrence or other types of metadata that could be related. And finally, going through millions of events does not make that much fun. Data simplification is a challenge in that realm. Our overall contribution is IVISA, a visual analytics approach for up to 1 million events in timestamped event sequences. We allow the interactive analysis of these sequences together with the features as a result of metrics, the interactive analysis of these sequences in comparison and in combination of interesting relation discovery in metadata. It's a multi-granularity approach, including an overview and detail analysis in many linked views. And finally, we have interactive data simplification support provided. Our methodology is technique-driven on the one hand and problem-driven on the other hand, which is a nice experience on our end. So it's a mixture of technique paper and the design study. For more, read the methodology in our paper. It was just fantastic to go through the data-first study and do a synthesis with technique-driven work. These are 6 cases that we were studying throughout the entire process, very, very different cases with one-to-one connect to individual experts. And you can see that the signature of events is super, super different. This is one of the examples how heterogeneous timestamped event sequences can be. There is one thing that I would like to share with you as a takeaway. We abstracted task using an actions, targets, and criteria method. It is very similar to the talk that we saw before. Can't wait to draw the connect. Here I show you, for example, a sort action that can be applied to different targets by different criteria. And what I mean with this is that IVISA supports 5 different types of this sort action. Sorting events by feature, sorting event sequence by groups, sorting event sequences by metadata, event sequences by features, and event groups by features. So it is not only a single sort, it is actually 5 different types of occurrences of that, all of them supported in our tool. And this applies for all 12 tasks that we abstracted. And this is just the signature of it using the triplets of actions, targets, and criteria by which a task is executed. We can also align these 12 tasks in a workflow. We identified in all 6 cases that segmentation and alignment can always be done as a pre-process because they tend to be rather static throughout the analysis. And then there is the core analysis part of 6 tasks, which are very info-whiz-like, and then 4 tasks, which are very much referring to data simplification aspects where a lot of visual analytics and interactive machine learning capability came in. I would like to refer you one slide for metrics. This is the beautiful world of statistics and other types of non-visual approaches to actually make sense from these types of timestamped event sequences. This was very much recommended by Ben, and my group did a very good job in implementing all these and providing these local or global features. And this brings me to the interface of IVISA. This is an overview of the system of event sequences, up to 1 million of them. There could be, for example, an attribute by which you can filter and sort, and then you can see here that the system changes the representation and other patterns occur. This is the visualization of metadata and the metadata relation discovery. You can see that we cross-cut any 2 pairs of metadata that you want. And you can see here that events, for example, very often occur in June and July. So a pattern that exists in the data can be explained by just using seasonality. And we're using small multiples approaches for a 3rd metadata criterion, which is in this case, the borehole. This is the details visualization where individual lines represent a single event. these lines are temporal features, and these are motifs that we extract from event sequences to simplify things. This is the feature analysis where people can select or deselect features, do normalizations and see the distributions of the features, and then they can interactively be used for clustering. This vertical line helps people to drill down to the number of clusters that are desired. Dimensionality reduction is provided to get a second perspective on that high dimensional space. And this is a visualization where the clustering is then contextualized in the views I showed you earlier. This is a filtering approach where a simple filter control panel leads to a reduced number of event sequences. And this is the substitution of events through motifs, where actually user has selected this particular type of motif. It is then popping up in the motif definition control. And what you can see here is that if you would apply that motif, then 2% of your data in the events would totally be represented by that motif, leading to a drastic simplification of your data set. And this is how this looks like. In this case, we have two motifs already active, and you can see how these two green and orange guys substitute the original event sequences and events just by using that new motifs. And this is the same in the visualization of the detail views. To evaluate our approach, we used 3 of the 6 case studies explicitly and also described them as case studies in the approach just to assess the usefulness of the tool. And we also did a user study with all 6 cases and all experts for assessing the utility. An interesting experiment was to actually see how people engage with the 12 or 10 tasks that are provided. And what you can see here is just the signature of order of things that, in this case, the photographer applied, which sort of with a start and an end, leading to quite some interesting patterns in the way how they walk through IVISA. To summarize, this is the presentation of IVISA, the first, in my opinion, or as far as I know, visual analytics approach for time-stamped event sequences for more than 1 million of events. It allows a lot of different types of analysis for different tasks. It allows simplification of event sequences through clustering, filtering, and motif detection, and it is generalizable for literally any domain where these types of data occur. To end, I would like open with an outlook. I stole a slide from my presenter before me 12 minutes ago. That's the first time I do this. One of the very few things that are good at a virtual conference. Thanks for bringing our taxonomy into play, because this is what I also want to do. So we actually did in 22 in parallel a work on a task taxonomy, and we came up with 23 tasks that do exist in total. And luckily and nicely, 12 of our tasks perfectly fit into this, and others can easily be derived. And what I can also do is use the generative power of the taxonomy to refer to the future work that can be possible. It's annotation of event sequences leading to an interactive machine learning task. Find similar would be an extension to information retrieval. We could predict, modify, or abstract to a higher level for state transition, and finally recommend event sequences. This brings me to the end. Thank you for your attention, and this was actually my presentation. Happy to take 1 or 2 questions.
Thank you, Jürgen. Thank you very much for this nice presentation and good presentation. I'm really sorry we're out of time. The 1 slide was too much. I have to take I would like to ask you to take the question in Discord and answer them later on.
That's absolutely no problem. Kudos to the speaker before me, and we can do everything in Discord.
Yeah, thank you. Thank you very much, Jürgen, again. We are now moving to a regular paper again, and it's given by Jung-Si Dank, and we still, it's about comparative study on fixed order event sequence visualization, Gantt, extended Gantt, and string line charts. The floor is yours.
Thank you, Sylvia. Hi, everyone. Welcome to my talk. I'm Junxiu Tang, and I'm very pleased to share our recent TUCG paper, a comparative study on fixed order event sequence visualizations, Gantt, extended Gantt, and string line charts. First, let me take apart the title and introduce the background and the motivation of this work. Event sequence is a sequence consisting of discrete events. These events can have featured attributes and values shown here as different colors and shapes. And fixed order event sequence means that the order of events is predefined and usually remains constant in each sequence. Although the order is fixed, not like many visual analysis work to find the frequent event order pattern in fixed order event sequence, there still exists a different among sequence, the time. For example, the time stamp of each event can be different. Moreover, the duration of each event can also be different, generating different temporal patterns and diversities. So such kind of sequence readily exists in real life. Let's see some scenarios. First, in a car assembly line, each car will go through several procedures. The assembly log for each car is fixed order event sequence. The second example is a public train schedule. The schedule is a fixed timetable, but sometimes there can be delay or cancellation. So the transportation log for each train is a fixed order event sequence. Another example is the biological process. For instance, the plant will go through several stages to finish a life cycle. Such a cycle can be considered as fixed order event sequence. And also, except for a long log data set with multiple sequences, a timetable can also be regarded as a single sequence. These events are predefined and fixed on the schedule. So to summarize the feature of fixed order event sequence, we state that in this data, the order of event is predefined and usually remains consistent in each sequence. The timestamps and durations of event instance having the same event type can be different. So when analyzing how precising this kind of data, we can find temporal patterns, analyze efficiency, and detect anomalies. Or sometimes we may just want to present the data for communication purpose. So visualization and visual analysis can assist in these requirements. For a fixed order event sequence, only those timeline-based visualizations can encode event types, timestamps, and duration. So they can visualize all the temporal data. And such kind of visualizations include Gantt chart, extended Gantt chart, and streamline charts. And Gantt chart were widely used in project planning and schedule comparison. Extended Gantt chart can represent complex event sequences. And streamline chart, also known as Maris graph, was used for transportation schedules, industrial process like warehouse order processing or assembly lines. So to the wide applications of these charts underscore their strengths in various usage scenarios. Thus, it's important to understand their performance and select the most appropriate visualizations. Understanding them is also a fundamental step to developing more efficient visualization methods in the future. So here is an overview of our work. We conduct 2 in-lab experiments with 93 participants to evaluate the effectiveness of these charts for visualizing fixed order event sequence data. And we evaluate 2 tasks, duration comparing and pattern finding. We use task error rate and the task completion time as the measurement in our study. To begin, we first define fixed order event sequence in math, given Allen's interval algebra and Megan's extended version. In our fundamental study, we only consider the serial fixed order event sequence, as this can control the experimental trails in a reasonable count. Based on the different combination of point events and the interval events, and also the gaps between 2 events, we can have 5 types of sequence. And here, in the name of sequence type, the letter P represents point event, letter I represents interval event, and the letter
There went something wrong?
Yeah, he left the meeting. Maybe some internet problem. I will check with him.
Thank you. We lost you somewhere.
Maybe we can first move to the next person because our time is also very limited.
Yeah, this is limited. This is true. I was just waiting if he is coming back, but it don't look like that he's coming back. Okay, I'm really sorry. We move on to the next talk, yeah? And maybe we finalize it if time allows it. And the next talk is given by Rita Borger, and it's about interactive hierarchical timeline for collaborative text negotiation in historical records.
Thank you, Silvia. So good morning, everyone, and thank you for joining this talk. My name is Rita Borgo, and I will be presenting on behalf of Gabriel Cantarera, who unfortunately could not attend the event. So without further ado, let's dive into the presentation. So what I would like to present today is the result of a work that we developed in the context of a very large project named the Quill Project. Quill is a research initiative which focuses on maintaining data sets related to foundational legal text with focus on constitutional conventions. Data are maintained to support both educational and research activities of humanities and academics and scholars. Quill datasets are structured as large multi-layered event sequences which include whole hierarchical and historical aspects related to the outcome of a legal convention. These include documents provenance, voting records, procedural decisions, and also details of all the negotiations that are related to the development of a document. Information are extracted from historical records, and they are digitized and used to build a relational database which contains all links to events, people, documents, sessions, which constitute the outcome of a convention. The structure of the underlying data is quite complex, and first, conventions documents are the results of hundreds of interactions which involve several actors over a large extended period of time. Second, while the conventions follow an implicit hierarchical organization, the entities within the hierarchy do not necessarily follow a sequential ordering. So in this context, visualization methods to be able to navigate such data are become a necessity. In the context of the Quill dataset in particular, it is possible to formalize conventions through hierarchical to a hierarchy which is characterized by three main levels. At the highest level, we have committees, that is groups of people which conduct multiple meetings, and each meetings decisions are made related to one or more documents. The second layer is represented by committee meetings, which are called sessions, and each session has its own list of topics and timelines of events. Events represent the final and lowest layer. Events are the only entity with an implicit sequential ordering. Events describe actions that occur within a session and that directly affect the document. This can be, for example, the creation of a document, amendments, discussions, decisions, and also the voting record. Events also include the list of people which are involved in a decision, as well as identifiers and relevant keywords. Events themselves can be interconnected, and this creates an additional dimension of hierarchical abstraction. Documents within events can also have connections, and this is due to the fact that within an event, documents can be created as copy of other documents or complements of other documents. And these sources can be referenced across multiple committees, resulting in further interconnections within the timelines. So designing in such a scenario is non-trivial. And in our collaboration with the Quill users, what emerged was the need to design a visualization that would be able to display timelines and event relationships across different levels within the hierarchy, but also at the same time able to provide a representation of the provenance of the informations which are themselves generated as a collaborative text development by multiple actors. So we were able to gather 4 main requirements. The first one was that the visualization should enable the users to have both an overview of the text and events related to the text over time, and also an overview of the overall flow of events in the datasets. Also, for any given fragment of text, the users should be able to follow its histories and identify its ancestors, children, and all the people which were involved in the reduction of that particular piece of text. The visualization should also be able to highlight relationship between entities like text, events, people, and topics, and also support identification of recurring patterns. And as final step, we were also asked that the visualization that we would produce should integrate seamlessly within the canons and all the interface already existing in the Quill platform. To the same discussion, we were able to identify 4 design tasks to satisfy the requirements. The first one was the use of multiple views. Multiple views allowed us to combine summarizations together with a level of detail that was needed to convey both provenance and entity relationship. Interaction at the timeline level to allow for an overview of most relevant events while providing information on demand. Selection and highlighting of elements which were of interest, and also elements which were connected by provenance to whatever was under analysis. And finally, the ability to provide context on demand, given the interconnection across the different texts and different documents belonging to different timelines. Additionally, the visualization should link and conform to canon and interfaces already existing within the system. So our visualization tool was then designed with 3 main areas in mind. The first one is the document path overview timeline, which shows the activities pertaining to the document under analysis. And it also allows to embed the document in the context of all the related documents within the data sets and the specific timeline. The second area looks at the development of a single document timeline, and this shows events organized according to the dates on which they occur. Events, they have their own hierarchy, which is displayed by hovering the cursors over an event, and this also displays a description box for the selected event. Selection of an event provides a visualization of all the relevant connections. Multiple events are condensed into one semantically meaningful symbol, and the symbol design was we were asked to prioritize amendment proposal events, then followed by other events such as approval, rejection, or further discussion. Finally, a document panel shows the document under analysis, the text under discussion, and also provides panels for a list of people and keywords involved in the analysis, in the reduction of a particular document. Selection of a segment of the text or a person name or keyword allows to highlight all the events that are related to the object under analysis. Now, just quickly looking at the tool in action in the document path overview. Let me see if I can start the video. Yes, in the document path overview, it is possible to see a document being referred to a different committee and discussed in the committee, then brought back to its original committee as part of a larger document section. Hovering over each document icon will further highlight which sessions discussed each document. In the single document timeline overview, instead, we have the possibility to inspect each sessions from the documents committee, which is laid out along a horizontal line, and also the sequence of events in each session, which are displayed vertically. Each session is displayed as an orange dot with the superimposed symbol that I mentioned before, and they represent text altering events, and they are stacked according to their temporal sequence from bottom to top. Hovering the cursor over one of the symbols shows connections and highlighting of other relevant information. The document panel supports interaction with the text, selection of specific word, or accessing information on related documents. The text viewer provides the full text of the document and all the relevant information. For example, removed fragments due to amendments or reduction. The document information panel shows a list of all the ancestors and children of the current document, including immediately relevant information, for example, committees and when the committees acted and what were the change. People and keyword panel contains a list of all the people and the keywords which are relevant to the specific document or specific text. Now, the tool development followed a user-centered design and evaluation. Our interaction with the users consisted of ongoing feedback from our lead domain expert and evaluation session with multiple other experts. We performed 3 rounds of evaluation at different significant milestones in the development. The first one was an inception workshop. The second one, an evaluation with a larger group of users of the system. And then the third evaluation consisted of domain expert interviews and workshop evaluation, which focused on evaluating the ensemble of the interface and its features as a whole. Overall, the tool received positive feedbacks in the evaluation sessions, and domain experts were effective in providing insights to guide the development, as well as suggestions that could lead to future work. The tool currently has been integrated in the Quill platform. Some future work will be focusing on supporting visualization of looking more at the multidimensional nature of texts as living entities that exist across different timelines. And finally, I would like to thank all my co-authors and thank you for your attention. And if there is any question.
Thank you, Rita, very much for the presentation. And I really enjoyed having these clear requirements and then the tasks and then the evaluation. It was really, 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 really nice. I just look in Slido if there are any questions. There is no question, but I have a short question.
Sure.
I was thinking, if you try to synchronize the different events and the text, it looks everything is very, very clear. There is no temporal uncertainty. Is this true? Is this so easy that you connect the different sessions and the different text? Is there no uncertainty temporal?
I lost you, Sylvia, but so the uncertainty is very much dependent on how much information are within the text. So for some of the texts, the uncertainty is actually some of the texts, the correlations are quite clear. So the corresponding visual representation is pretty straightforward. What the challenge is when we have items which appear in different timelines and they have different identifiers, but relate, for example, to the same group of people or to the same text, or if reduction. So the uncertainty is introduced at times when when we lack consistency across different committees and meeting session. The other layer of complexity is due to the fact that some of these documents are being analyzed and reduced across long period of times, which means that oftentimes the reductions are the reduction of a document across different time can introduce changes which are difficult to link back to what was the previous decision and the current decision due to a change in the context and also in the circumstances. So that is probably a bit more. It's more at the decisional level that is difficult to output as an extra feature to the data. Sylvia, sorry, I can't hear you.
Sorry, I moved it. Thank you very much, Rita. Thank you very much for the
You're welcome.
presentation. And we are limited of time. And I also saw that Jung Jiu is back.
Yeah.
We have approximately 5 minutes left.
Okay, I will briefly introduce the left part.
Yeah.
Thank
You
you.
were somehow lost.
I'm so sorry that the network is broken. And if it's broken again, I will share the recorded video. So we evaluate the 3 visualizations. And as for the condition, we have a lot of to consider. But for more details, please refer to the paper. And in conclusion, we have this number of trails in our study. And this is an overview of our experimental procedure and the interface. Yeah. And for experiment 1, here are some trail stimuli, and we have hypotheses, this and this. So let's skip the detailed results and just get an overview. We will have a takeaways in the end. Also, an overview: Streamline is good at task accuracy, while other 2 are good at time. And in experiment 2, we turn to multiple sequences. However, using the fundamental encoding of these visualizations, there are some apparent flaws, so we exclude those conditions. For more details, also please refer to the paper. And in finding similar timestamp patterns, we assume that the 2 charts exhibit similar performance because both charts has apparent visual cues. And the result is as following: in most cases, Streamline performs better. In finding similar duration patterns, we assume Streamline outperforms Gantt chart because the parallel lines in Streamline are more apparent. And the result shows that Streamline chart outperforms Gantt chart in most conditions, unless when the number of sequences is only a few. So let me finish the presentation with several takeaways. First, Streamline charts can be used in comparing tasks in IGI and II fixed order event sequence type to get a lower error rate. It can also be used to review temporal patterns in multiple PGP fixed order event sequence for good performance. And as for the Gantt chart and extended Gantt chart, they can be used in comparing tasks in fixed order event sequence with the few event type counts. There are values to optimize Streamline charts or its variants for interval events in multiple sequences, as in single sequence, it can have special advantages. On the other hand, we can make use of the unchanging event order of fixed order event sequence data in the other 2 charts. For example, grouping technologies in existing studies or sequential color mapping, but it will require further evaluation about the efficiency, about the task error rate, accuracy, and the task time cost. And also we can transform fixed order event sequence to better present the source data. For example, the data structure of II and PGP sequence may be the same, with the difference lying in how we interpret each timestamp and interval, typically based on domain knowledge. If domain requirements allow semantic transformation between events and gaps, this can provide a broader perspective for exploring the data. Since these 2 sequence types have distinct visualization forms, this transformation could offer better options for presenting the data, given the experimental results. And this work was supported by the funding above. And thank you for listening. Thank you, Sylvia. And we'd like to thank all the reviewers for their valuable comments, and thank the chairs and the student volunteers. And that's all my presentation. I'm ready to answer the question on Discord, maybe.
Thank you very much. Thank you very much. And I'm really impressed that you could proceed with your presentation and still convey your overall takeaway messages. This was really good. I'm really sorry we don't have any time for additional questions, and I would like to ask you to go to Discord to see the questions. Yeah? I would like to use the last minute to thank all the student volunteers that everything went so smooth. Thank all the presenters who took a little bit more time than expected because we didn't have a lot of time for discussion, but it's on your risk, not on my risk. Thank you very much. And we have a couple of challenging new talks in the near future. Thank you very much, and thank you for giving the presentations.